So guys, so what I was telling last class, the energy band formation. Okay, so in a semiconductor, we have this energy, right? We have something called valence band. This is called top of my valence band. This is my bottom of my conduction band. You see, right? Right. So what you told, the carriers are allowed to stay only in the conduction band or in the valence band. Okay, and we have total 4n electrons and 4n electrons and we have 8n states, right guys? Okay, so out of 8n states, there are 4n states in valence band, there are 4n states in conduction band. Clear, all of you? Okay, so at T is equal to 0, temperature T is equal to 0, okay, all the valence band is filled with, so at T is equal to 0, all the 4n state will have 4n electrons, okay, and all the conduction band is empty. You have 0 electron at T is equal to 0. So there is no carrier that is free to move at T is equal to 0. So it behaves like an insulator. Clear? Clear. And thing is, suppose this is my top of my conduction band. In between EC to ET, ET, the energy states are not uniformly distributed. It distributed over the energy like this. So we have shown this is my EC, this is my EV, this is my energy. If I want to plot the number of states, NE, right? NE is nothing but my distribution of allowed energy over the state. Okay. So over EC, if you see, they are distributed like this. What is the meaning? Suppose I was explaining, suppose I want to, so guys, this is the point where we have all doubt, okay? Again, I'm explaining. Suppose I want to, suppose the water is filled here, okay? Water is completely filled. Okay, so I want to find out at a height h1, this is my height h1, between dh, dh height, how much water is there, right? Guys, hello? Yes, so what is the water there at h1 between dh? So suppose the beaker is like this. Okay, so water is filled like this. Okay, so at this height h1, this is my height h1. Okay, this is the distribution of Ne, or this is the this curve. Okay, this curve. So this curve is nothing but my NH. Clear, guys? So I want to find out at this height h1, right? How much water is there between dh? This is my small dh, right? So come on, guys. Last time I told you how much water is there at a height h1 between the distance dh. How to get? This is the curve is given by n into h. So curve depend upon the height. So can now tell me how much water is there in between this? Please let me know.
You can take the integration from minus dh by 2 to plus dh by 2 of that function.
Perfect. Or if it is very small, if dh is very small, I can approximate it as like a rectangle. So it will be dh into the n at height h1, right? So the n at height h1, this is my n at height h1 means is this one, right? This is nothing but my n at height h1. This is my width. What is the height? Height is dh. So width and height. So I can approximate this as a rectangle, right? Whose width is n of h1 right? N of H1. Just guys, 1 minute. So this is understood, na? This is how to get the water at a height H1 in between DH, right? Yes.
Yes.
Yes. So similarly, here also, suppose I want to find out the number of energy state, okay, at a energy E1. This is my height of the energy E1, okay, in between DE. Okay. So I want to find out the number of energy states available between width D at a energy E1. Okay. How to calculate? So I will approximate this curve as a linear curve. Okay. So it will be, if you come here, it will be how much? NE1, right? NE1. Okay. So how much energy state are available at a energy E1 between energy DE, right? So how much I will get? NE1 into DE. Is it clear? Hello?
Yes, sir.
Yes. So if I want to find out what is the total number of energy states available, EC to E top, what I will do? I have to integrate from EC to E top. Then if I integrate from EC to E top, what is the number of energy level states I will get? Yes, quickly. I will get the total energy states in the conduction band, right or not?
Right.
So how much I will get?
4 and
400 state. Similarly, if I do the same exercise in the valence band, it will be bottom of valence band to the top of valence band. Okay, N E into D. Okay, this is conduction band, this is valence band. Okay, will be given how much it will give?
4.
4L. So is it clear to all of you till now? Hello? Hello?
Yes, sir.
Yeah, no doubt now. So finally, what we got is, okay, energy distribution. Okay, EC, EB. Okay, and if I want to approximate as a mathematics, okay, this is my NC. NC is nothing but allowed. This is an allowed state function. Okay, this is a distribution of allowed state function in the conduction band. Okay, it will be simply A1 into root over of E minus EC. Okay, so this A1 is equal to how much? 8 root 2. This is no need to remember for you. Okay, I am writing down whatever I got. Divided to H Q. Okay, so if I want to approximate the distribution function, okay, NC is nothing but distribution of energy states in the conduction band. It will come as a parabola. This is the equation, right, guys? And if I do the same thing in the valence band, okay, also I will get NB in the valence band is A2 into root over of EV minus E. Getting? So this distribution function in conduction band and valence band is approximated in terms of a parabolic function. This is the summary of this. Is it clear to all of you?
Yes.
Hello? Yeah. So clear. So till now what we have reached? So what we have reached is we want to find out the, in analogy, we want to find out the number of people staying in a 10th floor building, right? So this is my 10th floor. So this is my 9th floor up to this is my 1st floor. So this is what it gives. It gives in which floor or at what energy how many trucks are available. So this is nothing but at what floor how many rooms are available. This only this will give me. Clear? Yes. So I want to find out. I am giving an analogy. Okay. I want to find out number of people staying in the 10th floor building. So in this what you have got at what floor how many rooms are available. Similarly here how I got in conduction band at what energy level how many states are available. Clear? You got the analogy?
Yes.
Yes. Now what is the thing is now I got how many rooms at what floor. Then if I want to find out how many people are staying in the building, then what I have to do, in each floor there are rooms are available. So out of all the available rooms, how many rooms are occupied by people? That will give me my number of people staying, right, in that floor. Okay, suppose in 10th floor there are 5 rooms. So in 5 rooms, out of 5 rooms, what, how many rooms are filled, right?
Yes, yes.
Yeah, so that is nothing but my what fraction of available states. See, this is the states available, right? This is my state available. Okay, this is my state available. Okay, so out of that, what fraction of states available is occupied by the carrier? That will give me my number of carriers. Suppose in this, I told you this is nothing but, I told you, suppose I want to find out how many number of electron in the conduction band at a energy U1 between D. Okay, so what I have to do? So the total number of states are NE1 into D. This is the total number of rooms available. So into what I have to do to get the total number of electron? What I have to multiply? Yes.
Probability.
Probability. So this many rooms are available. Out of the out of these rooms, how many rooms are filled? That is the probability of this rooms is filled. Okay, this is nothing but my Fermi-Dirac distribution function. Okay, that we will discuss next. So if
Sir,
this
actually, what's the need to find in the between states? Like
no. There is no. See, what you want to find out the total concentration in the conduction band, but how to get total concentration? If I suppose if I know this, then I will have, suppose if I know this, okay, then if
Yes,
I know this, then I will add everything. Okay, add means nothing but integration. So this is nothing but the total number of electron at a energy U1 in between DE states. Okay, this is the number of electron. If I want to find out total electron, then I have to integrate. Right? There is nothing but I have to sum all the rectangles. Summing of all the rectangles means it will be integration from EC to E tau. Right or not?
that I understood, sir. I asked that because we all earlier it was said that they will actually occupy the lowest state possible. So we should just have to check the
See,
upper.
that's right. That's right. So that will be ensured by this Fermi-Dirac function. Okay. So then I will explain you this what this is. This is rooms available. So out of this rooms available, lowest state occupied will be ensured by this probability. If you go up and up, the probability will be very less. Even if you have a lot of rooms available, only minimum numbers of rooms will be filled.
Okay. Yeah, that function. Okay.
Yeah, that function is a probability. What it tell at what energy out of the available state, how many is filled. So if you go up and up, right, the probability will be less and less.
Okay. Fine, sir.
Okay. So we will discuss a little bit about this one, Fermi-Dirac function. Okay. So what is the Fermi-Dirac function? It will tell me out of the available states. So this do not tell you whether states are available or not. Okay. What it will tell you, if there is a available state, whether it is occupied or not occupied, it will tell you. Clear? What it will give you? Guys, so how many states are available will be given by the distribution function. That distribution function will be given by that NE will give you the how many states available. This FE will give you if it is available, it is occupied or not occupied. Clear? Clear. So suppose I want to plot this function. Okay. Okay. Suppose I want to plot this function. Suppose this is FET. Okay, this function. So guys, you see, suppose E is very high. Okay, suppose if I go to very high. Okay, if suppose E is very infinity, what will the probability function? Suppose E is equal to infinity, what will be ET? Come quickly.
0, sir.
Huh?
0.
0. Okay, so very good. FET T is equal to 0, right? Suppose my energy is equal to 0. Energy is equal to 0 means minus infinity. Okay. Then what will be my FET?
1.
1. Right? E by minus infinity will be 0, 1 by 1 plus 0. Right? Clear? So if I want to plot, okay, suppose somewhere here, don't know, will be, I will tell you what is EF. Okay. EF. Okay. If I want to plot at very high energy, right? So maybe I can say E infinity is nothing but my E top approximately. E minus infinity is nothing but E bottom.
Okay, now I got the point clear. Point
No,
out.
let me come to you. Okay. So if I plot, right, so at very high energy, the probability is 0. If you come down, at E is equal to EF. What is the probability?
0.5.
Huh?
0.5.
0.5, half. Right? So at E equal to EF, I will get a probability of this is nothing but 0.5. This is 0.5. At E is only very high, it is 0. So it will be 0.5 at E is equal to EF. Here, this is my energy. This is the probability. Okay. And at very negative, like in the bottom of the band, it will be 1. Okay. So it is 1 at the bottom. Suppose this is 1. So it will come like this. Clear? I am not doing good drawing. Okay. Okay. So what we are thinking? This is this function FET. I plotted over energy. Okay. So if you go to very high energy, the probability is 0. If you come down to EF, my probability is 1 by 2. If I come down to very bottom of the condition mat, it is completely filled. This probability is 1. Okay. Right or not?
Right.
And I have my conduction band somewhere here. So what it tell? What is this formula function it tell? At E is equal to EF, if t greater than 0, right? The probability of the state occupied is half, right?
Yes.
And if you go below EF, the probability of state occupied will go on increasing, right? If you go above EF, it will go on decreasing. That's what it will tell. Right or not?
Yes.
Right. Right.
Right. So this is all t is equal to 0. Suppose t is equal to 0. This is I plotted at t is equal to 0. T greater than 0. Right. So if I this is for t greater than 0. So if I want to plot the same thing at t is equal to 0, how it will be? T is equal to 0. This is 0. Right or not? Yes.
Infinity case again.
No.
0.
So at t is equal to 0, this is 0. If E little bit above minus EF, right? It will be 0. See, at t greater than 0, if E is greater than EF, clear? What will be FET? Little bit greater than EF, what will be FET? 1 by 1 plus E greater than EF means positive, right? It is positive by 0. It means it is infinity only, na? Equal to, sorry, infinity equal to 0. Is it clear to all of you? So at t is equal to 0, if the energy is little bit more than EF also, little bit positive, maybe 0.00001% also. Okay. So if it is positive, so 1 by 1 plus e to the power of some positive number divided by 0 will be 1 by 1 plus infinity is equal to 0. Clear, guys?
Clear.
Clear. So
Yes.
suppose if E is less than EF, what will be FET? What is the probability?
0 always, sir.
No, it is 1, right? See,
1.
1 by 1 plus, if E less than EF, it
1,
was
sir. 1, sir. Yes.
minus number, negative number divided by 0. So it was minus infinity, right? So e power of minus infinity means in minus infinity only, right? So 1 by minus infinity is 0, right or not? Hello?
Right, sir. Right.
Right. So sorry, 1 by minus infinity is 1 na? Oh. 1 by infinity is 1 na? Is equal to 1 by 1 plus 1 by infinity, right or not? Clear?
Clear.
Clear. So at t is equal to 0, all state above is having 0 probability and all state below is having 1 probability. This is the EF at t is equal to 0. Is it clear? So EF is a level at which whichever states are there above the EF are unoccupied and whichever states are there below the EF is occupied at t is equal to 0. Is it clear?
Exactly at E equal to F, we cannot say na, at T equal to 0 Kelvin.
So at E is equal to EF, it will be 0 by 0. It power of 0 by, so it will be 1 actually. At usually EF, if you see, it will be 1. So it is going from 0 to 1, in between it is half. Getting?
But
It is
0
going
by
from
0 is indeterminate from coming, na sir?
0 by 0 is coming indeterminate. Okay, but if you see little bit greater than 0 is 0, little bit less than 0 is 1. So at EF it should be 0.5 only.
Okay, means we have to take the average of this.
Yeah.
Okay, sir.
So here it will be 0.5. Okay, so what is the meaning of this EF? At temperature T is equal to 0, all the states, if available, above EF will be unoccupied. All the state below EF, if available, is occupied. Clear? Right?
Yes, sir.
Right. Right. So this is my probability function. What it tells? Suppose you see, suppose I am t greater than 0. Okay. Let me take another color. Okay. Suppose I am having t greater than 0. Okay. Okay. And if I want to plot the, this is my FET. Okay. If I plot the NE, right? How NE will be? NE, you know, like this. I don't know. Right? This is my NE, na? Over energy. Right?
Right.
Right. Okay. So what is the meaning of this one? Suppose if I say here that energy E1, that energy E1. Okay. What it tell? Even if this many states are available, okay, only this money is occupied. Getting? Hello?
Yes.
Because if you multiply Ne by Fe, if you will get the number of electrons available at E1 at between DE. Okay. So this is my Ne, this is my Fe. If I multiply these two, this multiply with this, you will get this only, na? This green and green shade, right?
Yes.
Right. Suppose
Yes.
if you go above, if you go above, if you see out of the available state this much, only this much is occupied, right?
Right.
So your concept clear now, got clear? Clear. So with this idea, okay, with this idea, if I want to find out the formula for Ni, okay, guys, you two should tell me quickly, very quickly. So you are now capable of answering this question. EC, G my EV, So this is my Fermi-Dirac function at t greater than 0. Okay, still I am not covering properly. Okay, this is my FET. Okay, I will draw the NE. This is my N. This is my N in conduction band, distribution function in conduction band over M represent T. Okay. Then if I want to find out, this is my top of my limit. So tell me now what is the concentration of electron in conduction band? Okay. So can I write it down? Should be equal to, so Ni is nothing but concentration of electron in conduction band is, I have to integrate from EC to E top, right? Number of states available, okay, into maximum states occupied D. Is this clear, guys?
Clear.
So if I do this, I will get, you have to multiply this thing, right? Multiply these two things. Okay. So whatever area will come, right? Still the states occupied. Right or not? So if I do this, okay, then you put the formula for NC of T, you put the formula for Fermi-Dirac function, okay, then you will get a closed loop. I don't want to solve the mathematics for the time interest. Then you can solve the mathematics. You can let me know if you are not able to get. Okay, so we will get a closed loop expression. Okay, so it will be how much? Suppose EC to ET. What is NCE? I got N1 into root over of E minus EC. What is FET? FET is nothing but 1 by 1 plus exponential of E minus EF by KT into dE, right? This integral you have to solve to get the number of electron in the conduction band at any temperature. Clear?
Clear.
Here. So you have to
Sir,
take,
sir, most of the time in Donald-Niemeyer also that that overlapping area is actually approximated in the right side, and then they take the area of this
yeah, definitely. Right side means what? This is just for showing you. Okay. So here I have to show you.
Is
Okay.
that approximation is good, sir, for taking that
See, it is
overlapping
not,
area?
there is no approximation here. Simply it is multiplying NC and FE. These two curves is multiplying. The resultant of
Yes.
this multiplication just they are showing here. That's all.
Okay. Means there's a pictorial scene actually, right?
Pictorial scene is nothing the right side or left side. They just want to show you the multiplication of these two curves, this and this, in a curve. So if you multiply
Okay,
this
sir.
and this, you will get a curve like this. Getting? So see above in below level, the NE is smaller, so the NE shape is coming. Okay, just let me draw it. I am coming to that point you have told me. Okay, so in a lower level, NE is small. Okay, so it comes like NE. In the top level, FE is more, so it's looking like FE. This is if you just multiply FE and NET, if you want to plot these two just multiplication, if you want to plot, it will come like this. If you integrate this, this will give you my total number of electrons. Okay, this is just a pictorial representation of these two curve multiplication. Nothing right or left in this. Okay.
Okay, sir, fine.
And we have to take following approximation to solve this question. This will be asked in the exam to you. Okay, what are the approximation you have to take? First one, we have to tell ET should be infinity. So we will put ET comes to infinity. Why? Because guys, you see, if you go above and above, right, after a certain time, the already the probability is 0. So even if you take infinity or a little bit more, that doesn't matter, right? So after this point, suppose this is E top. So after E top, there is no probability of having the electron. So even if you take infinity, it doesn't matter to you, na? Yes.
Right.
So I can approximate ET terms infinity because after ET, the probability of occupation is 0. So even if ET comes to infinity, it doesn't matter. Right or not? Means
Not ET comes to infinity.
see what I'm telling now. This is the exponential curve, right? Exponential curve. If you go above energy level, right, the probability will be very small.
Yes, sure.
Okay, so since they are very small occupation, okay, so approximately I can tell it is comes to infinity only, because even if you put it is will exactly top of the balancement or infinity, it will not give you so much of difference in the calculation. This is approximation. Okay.
Okay.
Second is very important. It's called Boltzmann equation. Okay, Boltzmann approximation. This will come in the exam. There is so much of unstable in my writing actually. Approximation. Okay, how did it tell? If E is greater than EF, if E minus EF is greater than equal to 3 kT, then I can approximate the Fermi Dirac function in the following way: 1 by 1 plus exponential of E minus EF by kT. Okay, so if E minus EF is greater than 3 kT, okay, this exponential function will be far more than 1, right?
Sure.
Because it will be exponential 3. E minus EF greater than 3 means it will be more than 3. Right or not? So this term will be more than 1. So I can approximately approximate as 1 by exponential of E minus EF by kT, or it will be written as exponential of minus E minus EF by kT. Okay, this is my Boltzmann approximation. Clear? So they will ask in the exam, Boltzmann approximation will be applicable when E minus EF is greater than 3 kT, 2 kT, 5 kT. Then you have to remember it's 3 kT. Okay. Okay. So another thing is another approximation is if E minus EF is less than minus 3 kT. Okay. So we can approximate. You see, be 1 plus 1 by 1 plus x. If x is very small, right, it can be approximated as 1 minus x. If x is very small. Okay. Similarly, if E minus EF is minus 3 kT, what will happen to FET? Equal to 1 by 1 plus exponential of E minus EF by kT. So if E minus EF is very less than minus 3 kT, right? Then what will happen? This will be very small, right or not?
Yes.
So I can approximate it as 1 minus x means 1 minus exponential of E minus EF by kT. Clear?
Okay.
This is my Boltzmann approximation. This and this. These two are the Boltzmann approximation. If you are far above EF, then you have to put this one. If you are far below EF, you have to put this one. Clear?
Okay.
So in this, suppose this is my EF. I don't know where EF is. EF. Suppose if my energy, whatever energy above 3 kT. Suppose this is my 3 kT. 3 kT. So whichever there above 3 kT, I can approximate in that level as this one. Clear?
Okay.
And the energy level below 3 kT of EF below means this range, entire range I can approximate as this curve. Clear? This approximation?
Clear.
Clear. Okay. So if you put all this approximation, okay, if you solve this value of Ni, how much you will get? Ni if you will get okay. So Ni will be okay if you do all the approximation, okay, you will get 2 into 2 pi at divided by s square or 3 by 2 into exponential of e EC minus EF divided by KT. Okay, this is the expression you will get if you solve the integration. Getting guys? Where Mn is the effective mass of electron in the conduction band. I have already explained you what is effective mass.
Yes, yes.
Right? So it is actually I have written here. Okay. See,
We don't need
this
to
is
remember this, right? Sir?
no. I will tell you. I will tell you. No need to remember. Okay. I will tell you. Okay. See, you don't try to remember anything in this course. Okay. That is my aim. So this is like you see, I got this into this. Okay. So if you see this, what did it look like? What did it look? What did this looks like to you?
Decaying exponential.
Pardon me. Can you come again? This is nothing but my Fermi-Dirac function at E equal to EC. See, at E equal to EC, this is my Fermi-Dirac function. Na? Okay. If I want to write my F EC at E equal to EC. Okay. Have right?
Oh, yes, yes, yes.
Okay. Exponential of minus E minus EF. What is E? E here is EC. EC minus 2 minutes, just a minute. ठीक है भूल पाइला ହେଲା हाँ so EC minus EF by KT I don't know
Bottom of conduction band, right, sir?
EC is bottom of conduction band, right? EC.
Okay,
Okay. So fortunately, what you got? You have done a lot of calculation, putting all the approximation. What you got here? This is nothing but your Fermi-Dirac probability at the bottom of conduction band. Right? That is right or not?
clear, clear.
Here. So then, what will happen? I need one more page to explain you. Okay. So maybe I have one page. I can explain. Okay. So I got Ni equal to NC into F EC into T, ECT, right or not?
Right.
Right. So this is nothing but my probability distribution Fermi-Dirac function at ECT. Okay. So whenever I multiply a probability by some number, I am getting the concentration every time. Right or not? Hello? Hello? So am I audible?
Yes, sir. Yes, sir.
Am I audible?
Yes, 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 sir.
So what I am telling, you got some NC multiplied by FeCT, right? So this is my concentration of electron in the conduction bed at any temperature. This is my concentration of electron at any temperature, right? Okay, NC. NC is nothing but, what I am telling, I want to tell something about NC. NC is called effective, okay, density of states. Like I showed you effective mass, this is called effective density of states. States at conduction band edge. Ready? So this is effective picture. So what it is telling? Okay, if I have at NC, this is my EC, okay, this is my EC, okay. If I would have been NC number of states available, Okay, and if I multiply the probability of occupation FECT, then I would have got the concentration in the conduction band. Okay, but NCT is just a virtual picture, just telling you, because I got the mathematics like this, then I'm just using this mathematics to make you understand better. Okay, so this we got. What is the meaning? NCT is the effective density of states if there are NCT number of states available at EC. Then if I multiply it with the Fermi-Dirac function at EC, then I will get Ni. Clear, guys? Hello?
Okay, so the total number of
See. Actually, the actual number of states are actually at NC. I don't have this. Actually, at EC, my NC is. You see the at EC, I don't have actually this many states. Okay, but after mathematics, I got this mathematics is like this, NC into this. So what I'm telling, it is like it is like mathematically it is looking like at NC I have this many number of states, to which I multiply the probability distribution function, I got the concentration. It just mathematically it looks like to you, right or not?
okay.
So I can say this is like a effective density of state if it would have been at the conduction band. If I multiply that with the probability, I will get the total concentration. So this is just like to remember this mathematics. This is like NC is the effect if it would have been there. Okay, it is not there presently. So this the mathematics you got after solving the equation, after integrating all the things. Okay, after integrating you got this formula. Getting?
Okay. Finally, after taking the integration, we'll arrive
Get
in
this
this,
formula.
right?
So then this, whatever I'm getting here, whatever I'm getting is a constant. Okay, you depend upon temperature and effective mass, everything. So that's the part I'm just telling you. It looks like there may be, it looks like it's effective picture. See, this much states are available, but it's not actually right. Actually, you've seen the distribution clear. This is the distribution. It's not there, but this is a virtual picture to you.
Okay,
Yeah.
sir. We came into that conclusion.
Yeah. So this
Okay,
is the effective picture. Okay, effective picture.
Okay.
Like effective mass, right? This is not the actual mass, right? This is effective picture.
Okay.
Effective picture. Okay. What is the real picture? Real picture you know, na? Real picture is if in EC, okay, this is my NC, okay, then this is my probability density function, okay, then if you multiply these two, I'll get, if you integrate, I will get this. This is the real picture. This is real. Okay. So in mathematically, how did it done? If there is NC states at this point, if I multiply it with FECT, then I will get this concentration. Clear?
Clear.
Okay. So all of you clear now? Hello? Yes. So thing is, it's very important formula. Okay. Ni is equal to Nc into exponential of minus Ec minus Ef by Kt. Okay. This is nothing but F Et at Ec. Here, this is the Fermi-Dirac function at the conduction band. Right or not? This is my Fermi-Dirac function at the conduction band at temperature. Clear?
Clear.
Okay. Clear? So this is NC is nothing but effective density of state function. Okay. So now you remember, don't forget this thing. So NC is proportional to T to the power 3 by 2. Okay. This is some constant into T to the power 3 by 2. It depends on temperature. Clear?
Clear.
Okay. So now I want to ask you, where is the Fermi level? If somebody asks you, I told you a lot about the Fermi level, right? Then where it is situated? So if I want to, you just logically, you just tell me, this is my EC, this is my EB, this is my EB, bottom conduction band, EB, this is E top. Okay. heat up. So guys, I'm just telling where this EF is located at any temperature in intrinsic semiconductor. Okay, in intrinsic in okay. So can this Fermi level be located here inside the conduction band? Can it be? Think. Hello guys, please.
Uh,
Can it be inside the EC? If it is there, what is the problem? If not, what is the issue? If yes, yeah, tell me the reason. If no, you tell me the reason.
I think it can be possible because below that level, everything is occupied.
At T is equal to 0, right? So if suppose if it is inside the conduction band, what is the EF? EF is above EF at T is equal to 0, right? Above EF, all are unoccupied, right?
Yes.
And below EF, everything is occupied. Here, but what is the meaning of this? At T is equal to 0, in conduction band we have some electrons. Is it possible? So if the Fermi level inside the conduction band at T is equal to 0, what is the meaning is this many number of states are occupied, right? What it meaning is below EF states are occupied, right or not?
Right, right.
Right. So but the thing is, you know, in conduction band the total number of electrons is 0 at T is equal to 0. There is no energy to lift the electron from valence band to conduction band, right or not?
Okay, okay, okay.
So it cannot be in the conduction band. Clear?
Clear.
So can it be in the valence band? All of you are getting or not getting, guys? Chetan?
Yes, sir. Getting.
Getting. Okay. So tell me, can it be inside the valence band? See, if it would have been in the valence band, okay, what will happen? We know above E equal to EF, all states are unoccupied, right? That means these states are empty. Means we have holes in the valence band at T equal to 0. Clear? Hello? If EF would have been in the valence band, what is the meaning is at T is equal to 0, all states are vacant. That means we have holes in the valence band at T is equal to 0. Is it fine to you? Hello?
Audible, sir.
So what my question is, if the EF would have been inside the valence band, then you will get some holes at T is equal to 0.
Okay, okay. Yes, yeah. Holes.
So that is not possible, right? At T is
No,
equal to
no,
0,
no, no.
so all the
Yes,
states in
yes.
the valence band should be filled, na?
Sure.
So that
So
should
it
be
should not be there.
should not be there, right?
Now I got the
Definitely
point.
it should be in between EC and EF. Correct? Clear?
Clear.
So if it would have been in EC, there will be 3 electron at T is equal to 0, which is not possible. If it would have been in valence band, there should be 3 hole in the at T is equal to 0, which is not possible. So definitely it should be in between EC and EV. Okay. So now, what I'm claiming, it should be approximately at the middle of the conduction band, middle of the energy gap. Okay. Okay.
Clear.
And if it is clear, now you should tell me why can't it be towards, can it be like here towards conductor EF, towards CC in the middle in the energy gap, can it be towards CC? This position is possible? Huh? It's not possible because if EF would have been close to cluster band, right? So what will happen? You will get a curve like this. Here half we got, then here 1. Okay. Suppose EF is, this is the position of, suppose this is the position of my EF, this is my FET. Suppose exactly it is in the middle. Okay, suppose it is exactly in the middle. How you will get? You get so here it is half, right? It is half. So we'll get like, okay. What it will tell, right? Tell if it is close to the conduction band, you will see the number of electron at T equal to 0 will be more compared to the number of holes.
Sure, sure.
So it cannot be in the towards conduction band, towards, it should be exactly near to the middle of the conduction band, near to the middle of energy gap. Okay, if the EF towards EC, then I will have more electron than holes. If the EF is towards valence band, I will have more hole than the electron, right?
Okay, okay.
Okay, so it should be in the middle of the energy gap, approximately. This is the location. Okay.
Yes,
So this is the topic, location of Fermi level by simple reasoning. Okay. Clear?
Clear.
Clear. Okay. So now I want to find out the number of, we got the number of electrons at Ni. Okay. I want to find out the number of holes. The similar way should be equal to Ne is the density of state function into the probability that a state is not occupied. Okay, FET is the probability of occupation, which 1 minus FE should be probability of non-occupation, na?
Yes, sir.
Right? So in a similar way, if I do the integration, I will get some constant into this. So it's nothing but NV into exponential of this one. Okay, so it is also looking like the F at EV T, right? This one. Okay, so the number of holes is nothing but NV into exponential of minus EF minus EB by KT. So this NV is nothing but effective density of states at valence band. Of states at valence band. Okay, guys.
Clear, clear.
So suppose like in this, suppose at EV, okay. Suppose at EV, okay, I would have been, there should be NV number of states. Then if I multiply this NV number of states by this Fermi Dirac function at EV, then I would have been getting the whole number of holes. Clear?
Clear, clear.
Clear. Okay. So also you know, at equilibrium in an intrinsic semiconductor, the number of holes is equal to number of electrons, right or not?
Right.
So it should be Ni equal to Pi, right? So then if I multiply Ni Pi, right? So this is my Pi, this is my Ni. Ni I know, Ni is equal to, I know. If you multiply, right, you will get like this. Okay, nothing but let me multiply for you. I have some place here. Okay, so I got Ni is equal to Nc exponential of minus Ec minus Ev Ef by Kt, right? What is Pi? Pi is, please tell me what is Pi? Effective density of state into exponential of minus of Ev E minus Ev. Guys, you are getting? Hello? These two are getting?
Yes. So the second one is EF, right? E
Yeah.
minus EF in, so EF minus EV. Last time you have
Perfect,
shown
perfect.
like that.
Should be EF minus EV.
Yes.
Right? Okay, see, also remember how not to do mistake. See, we know this is a probability function. right?
Okay.
So this cannot be greater than 1. Okay.
Okay.
We know EC at EC in the above, EF is below. So it should be EC minus EF, so minus negative, so that it will be a less than 1. If I write EF minus EC, it will be greater than 1, right? Similarly, here also you see, this is a probability function, it should be less than 1. So we know EF is above, EB is below. So EF minus EB, I have to take negative, so that I will get less than 1. Clear? Hello? Hello? Is it clear or not clear? Hello?
Just thinking,
See,
sir.
what I'm telling, we know if I multiply the effective density of state by a probability, I'm getting the concentration.
Yes, yes.
So the probability should be always less than 1 or not.
Sure, sure.
So that's why I'm putting EC minus EF. EC minus EF is positive number.
Okay, okay.
So then positive number I put negative. That means 1 by some positive number it will be less than 1.
Less than 1. Okay, okay, okay.
Similarly, here also you see EF is above, EB is below. So EF minus EB will give you greater than 1. So I have to do 1 by this. So I have taken a minus.
Okay, clear, clear.
So that you will not do any mistake in the exam. If you understand this point, this is a probability, this is density of states.
Okay, okay.
Okay. So if I do Ni into Pi, what I will get Nc into Nb into exponential of, you see, EC minus EF minus plus, EF is plus here, EF is minus here. So EF will get cancelled. I will get minus of EC minus EB by KT. Clear?
Clear, clear.
Equal to NC NB exponential of minus EC minus EB is nothing but energy gap, right or not? It should be
Right.
energy gap by KT. Okay. Also, I know the number of holes is equal to number of electrons, right or not? So I know
Right.
Ni is equal to Pi.
Okay.
Pi. So I can write this Ni is equal to Pi. So I can write Ni into Pi means Ni into Ni only. So I can write it equal to Ni square. Because in intrinsic semiconductor, Ni is equal to Pi. Number of electrons is equal to number of holes. Clear?
Okay. Okay.
So my Ni will be equal to square root of this means root over of Nc Nb into exponential of minus Eg by 2kT. Clear?
Clear, clear.
Here. So you see this. So Ni Pi is equal to Ni square, that you know, and it is equal to root over of Nc into Nb in the exponential of minus Eg by kT, root over of Nc Nb exponential of minus Eg by kT. Clear? Clear. So like
Two-
I ask, tell me.
By 2 KT was there.
2 kT
The
was
last
there.
step.
It is there, definitely it is there. So see, actually I don't remember any mathematics, right? So you should remember something. Like I know Ni is like this, Pi is like this. I know Ni is Nc into this, Ni is Nc into this, Pi is like this. So in exam, you need not to remember this Ni square, because we know Ni should depend upon a state function into probability. Then you have to multiply these two. Even if you do some mistake, you will recover in the exam. If you remember very totally like remembering phone number 94378, if you remember like this, you're definitely not going to answer properly, right or not?
Sure, sure.
So you have to understand the thing. Ni is Nc into probability, Nb into probability. Then you multiply, then you have to get this one. Okay. Then even if you forget, you can derive very quickly. Clear?
Yes, sir.
That's why you have to derive everything. See, even if you in signal system, okay, there is something called Fourier transform. So Fourier transform of AT is equal to 1 by A, x by A. You should not remember at all like this. Okay, Fourier transform of T by A is equal to A into number of. Like if you remember like this, you're definitely not going to answer in the exam. Okay.
Yes, sir.
So if f of t is equal to f of w, how f of a t is equal to 1 by a f of w by a, that you have to derive. Then you will get a feel how it would have come. So even if you forget, you can easily derive in the exam. So
Yes, sir.
signal system, there are hundreds of formulas will be there. Don't remember anything. Control system, the raise time, fall time, this bandwidth. Okay, so what is it called, peak time? All things are there. So first thing is you should derive this thing, how the peak time is coming. If you derive once, it will be imprinted in your mind. You need to remember the thing.
Yes, sir. Sure.
Okay, so not only for this subject, any subject, don't remember any formula. But at least you should know the derivation, how it would have come. Okay. Okay. So the question, one question is log Ni versus 1 by temperature. Tell me how it will be. What it will give? What it will give? Like I asked this question, right? So if you take log Ni is equal to log of root over of Nc Nv. So it will be log, if I do, minus Eg by 2 kT, right? So
Yes, sir.
log Ni versus 1 by T, okay, will give me what? So we plot log Ni versus 1 by 2. The slope is nothing but minus Eg by 2k. So if you take a semiconductor, if you plot concentration log with respect to 1 by temperature in different temperature, then the slope of the curve will give you the idea of the energy gap. Clear?
Clear.
This is a favorite question by any examiner. Okay. The slope of this curve will give a mobility, energy gap, concentration. You have to, if you know this, you could easily tell it is Ag by 2k, means it will give the energy gap. Okay.
Okay, sir. In the band theory, in the bond theory also, it was like
It is
energy
like
gap.
Ni is equal to number of atoms into each atom heated by a particle, nothing but Eg by kT.
Okay.
Right. This is a bond energy, and to break the bond, so this is probability expansion. This is probability. Okay. This is probability. Okay. Probability. So each atom into each atom is one bond will broke. Probability of Eg by kT.
Yes.
Also we got Eg only. Clear?
Yes.
Okay.
Clear.
So see, since I know how it come, I could write in front of you quickly key number of atom into probability. You should not remember n into p divided by 2. If you remember, we are gone, na. Okay. Okay. So with this thing, you remember this Nc and Nb rate is not constant. Okay. Nc depend upon t to the power of 3 by 2. Nb is depend upon 3 by 3 by 2. Okay. You see this formula. Nc depend upon t to the power 3 by 2. Similarly, Nb is depend upon 3 by 3 by 2. Okay.
Yes.
Okay. Also, one more thing you remember, the Pi in Nb is effective mass of hole. Okay. And in Ni it is effective mass of electron. Okay. So one question will come to you exam. Okay. So Nc is equal to Nv. Okay. Nc greater than is equal to Nv. Nc less than Nv. What should you write? Reading my question. You see, here Nc, if you see this one, okay, this is my Nb, right? What is Nc?
Right.
Nc is equal to, I am writing here Nc only, which is equal to 2 into 2 pi mn kt by h square, the power of 3 by 2. So if you see Nc and Nb at any temperature, T is constant, H is constant, so everything is constant. But here effective mass of hole, effective mass of electron. So you know the effective mass of holes is more than or less than electron?
More.
More. So at any temperature, definitely Nb will be little more than Nc. Clear?
Okay.
Guys, all of you clear? Hello.
Clear.
So this should. This is a question. Okay. So I'm telling some questions only while explaining things. Okay. This is the question in the exam.
Okay.
Okay. So there are many questions I need to solve. Okay. I put it in the end. So with this, I am completing the energy band model. Okay.
Okay.
So I have half an hour. I will introduce you what is called extrinsic semiconductor. Fine.
Okay.
So guys, all of you are getting bored or anyone getting bored?
No, sir.
Sec. Hello, Sec. Chetan.
No, sir.
Okay. So in half an hour, I will introduce you what is called extrinsic semiconductor. Okay. So we'll take just 1 minute of break. I will come from little drinking water and we'll start. Okay.
Okay. Sure.
Hello. Am I audible? Hello.
Yes, sir.
So today my voice is clear, na? It improved or not compared to last class?
Surely it improved. It improved a lot.
Okay. So guys, what do you mean by a extrinsic semiconductor? So in extrinsic semiconductor, we are deliberately introducing impurity inside the semiconductor in order to change the concentration. Okay. So whatever concentration you are here, right, getting, whatever concentration you got here, okay, this one, okay, it depends upon temperature only. You don't have any control, right? Right or not?
Right.
So, but I want to have control. Like I want to get as many concentration of carrier as I want. So can I control other than temperature?
Yes.
Yeah. Suppose there is one device you have given to the market. Okay. You will tell you should expose the device to this temperature, then only it will work. Is it the right thing to tell the customer?
No way.
Okay. Suppose you are in Himalaya, somebody is in suppose Delhi. So in Delhi it will work, in Himalaya it will not work. Okay.
Yes.
So thing is, I want to change the conductivity as per my wish. Clear?
Clear.
Clear. So that is the way we are introducing some external impurity into the semiconductor in order to change the conductivity. Okay. So first we will discuss the bond model qualitatively. Okay. So what is the thing? To a silicon crystal, we are passing very silicon is what? Group 4, na? Right?
Yes.
So group 4 means what? They have 4 electron in the valence band, valence orbit. That's why we have 4 bond, right? Each silicon atom is having 4 bond, right? So you see, this is my silicon atom. Okay, we have 1, 2, 3, 4. It have 4 bonds, right? We have 4 bonds with the neighboring silicon atom because it have 4 electron in the valence orbit. Right or not? Hello?
Hello. Yes.
Hello? Pardon me?
Yes.
Yes. So what I'm telling, each junction is a silicon atom. Each silicon atom bonded to 4 other silicon atom by a covalent bond because it have 4 valence electron state. These are the 1, 2, 3, 4 bond. So each silicon atom makes 4 bond with neighboring silicon atom because it has 4 valence electron. That's clear or not?
Clear, clear.
Clear. Suppose we'll introduce a high volume of phosphorus gas. Okay, phosphorus into the semiconductor. Phosphorus is group 5, right? Group 5. So it have 5 electron in the valence band. Okay, what it will do? The phosphorus have a tendency of kicking the silicon of its own side and occupying its space. Clear? So whenever we are introducing the impurity as a phosphorus, which is the group 5 element, what it will go? It will go inside the semiconductor and it will kick the silicon from its own side and it will occupy the side. Suppose you have introduced phosphorus, okay, it have gone here. So earlier silicon was there, it have kicked the silicon and it have taken its place. Okay, clear?
Yes.
And since phosphorus having 5 electron, it have made 4 bond with the 4 silicon atom. Okay, so the 5th electron is not bonded. Okay.
Yes.
Okay, so at T is equal to 0, so at T is equal to 0, what will happen? This phosphorus will make 4 bond with 4 silicon atom and it will have one more extra electron. That's right or not? Where it is
Right.
group 5. Okay, and this extra electron what will happen? What will happen? It will keep revolving around the phosphorus like this. Okay, at T is equal to 0.
Yes.
And it need, this 5th electron need very little energy in order to become free. Okay. Earlier, to break a bond, I was needing 1.1 electron volt by bond energy, but the 5th electron was revolving around the phosphorus. It need very small energy in order to detach from the phosphorus and getting free. Clear?
Clear, clear.
So whenever the electron is free, since the phosphorus has given 1 electron to the crystal, so it becomes positively charged because it has given one electron, right or not?
Right, right.
So I can say in this silicon crystal, the number of phosphorus atom, okay, so it need very small energy, right? So at T is equal to 0, all the phosphorus atom, okay, will have 1 electron revolving around the phosphorus, right? So if T is little bit greater than 0, very small energy, okay, the electron will liberate, okay, the phosphorus will become positively charged. Okay, so at T is equal to 0, T greater than 0, P become P plus, and it will, so at T greater than 0, what will happen? The phosphorus, what will do? It will give 1 electron and will become positively charged. Clear? So the phosphorus will give 1 electron and it will become positively charged. Clear, guys?
Clear.
Clear. So each phosphorus, suppose each phosphorus give 1 electron to the conduction band or for making the carrier free, 1 phosphorus gives 1 electron, right? But there is no hole, na? So whenever the electron is liberated, the phosphorus become positively charged, but there is no hole, na? Right or not?
Right, right.
Right. So whenever we introduce phosphorus, it gives 1 electron to the conduction band, but not the hole. Right? It gives only electron. Right?
Right.
So since it gives only 1 electron to the conduction band, it is called N-type impurity. Right? Impurity. Clear?
Clear.
Clear. So, and this electron needs only 0.045 approximately. Okay. eV to get detached from the phosphorus. Okay. So earlier silicon bond is how much? Is 1.1 electron volt. Okay. So even if some 1 or 2 collision also, this electron will liberate. Right or not? So here you need at 300 K 42 particles. Here 1-2 particles also will collide, they will liberate. So it's very easy to, so I can say at room temperature, almost all the phosphorus will give 1 electron to the conduction band, right or not?
Right. Sure.
Right. So this you compare the energy. Okay, we need this much of energy, we need this much of energy. Okay, so if I want to plot, the concentration versus temperature, right?
Yes.
Okay, this is my concentration, N0. This is temperature. Okay, so N0 means the concentration of electron. This N is nothing but N-type semiconductor. Okay, this N is nothing but electron. This O is nothing but equilibrium. Okay, so N0 means concentration of electron in a N-type semiconductor at equilibrium. Clear? Hello? Clear or not clear?
Clear.
Then N0. Okay, so what will happen if you increase temperature, right? This phosphorus, okay, will start getting ionized. Okay, so what will happen? The electron will go on increasing. Clear? Because in this range, what will happen? Whatever phosphorus we have introduced, they will start giving the electron to the conduction band. Clear?
Clear.
Okay. So after a certain time, what will happen? All the phosphorus will give energy, will give electron. Okay. So my concentration will become constant because all the phosphorus will have ionized. Okay. Clear? Hello? Hello?
Can you repeat, sir?
What I'm telling, when you increase temperature, right, this electron, right, which was revolving around the phosphorus, okay, so they will start giving the electron to the valence band. Okay, so this electron, so suppose here also, so all the phosphor atom will start giving one electron and become positively charged. Okay, so when you increase temperature from 0, okay, slowly all the atom will give electron, so my electron concentration will increase when I increase temperature. Fine.
Yes.
And after a certain point, okay, what will happen? Whichever phosphorus we have introduced, all will be ionizing, means giving the electron. That means now at this point, even if you increase temperature, there won't be any increase in concentration because all the phosphorus is ionized. Clear?
Okay.
Okay. So now what will happen? But see, suppose this will be maybe suppose 10K or 15K. Okay. But here, this is generated because of phosphorus is ionized. Okay. But to break the bond, I need more energy. Okay. So I have to go more high temperature. Right. Till now, bond breaking things is not coming. Only I got electron in the conduction band without hole. Clear? Till this point, I got only electron in the conduction band. No holes. Right or not?
Right.
Right. But what happened? When you increase temperature, right? Also, there will be some bonds that will break. Right or not?
Right.
So if you go on increase temperature, they remain constant. After a certain time, this is because of phosphorus ionization. Okay, here at this range, all phosphorus are ionized. Okay, but there are also very little thermal generation, right? Which is not shown in the figure. Okay, but if you increase temperature, what will happen? This thermal generation will increase, right? Because after a certain temperature, right, the concentration of due to thermal generation will start exponentially. Right or not? Like we have seen, Ni is proportional to exponential of temperature, right? What will happen after certain temperature? The concentration due to the thermal generation of bond breaking, I can say intrinsic concentration will start increasing. Clear? So after this
Clear.
point, okay, this is due to the thermal. Okay, thermal generation. Okay, so this will start increasing. Okay, so this is my electron concentration, right or not? So after this point, the electron concentration will increase. Okay, this is my nothing but electron concentration. Electron concentration. Okay, what do you mean by thermal generation? The number of holes is equal to number of electrons or not?
Yes, yes.
Yes. So up to this temperature, this will go on increasing exponentially. Clear? So what will happen to my total concentration? It will be the concentration due to the ionization plus this much
Yes.
whatever we got. So it also will go on increasing. Clear?
Yes, yes, yes.
Okay. So up to this point, only impurity ionization. Okay. After this point, the thermal generation will come into picture. Electron and hole will generate in pair, and it will increase exponentially. Okay. So this is nothing but impurity. This is because of thermal generation. Okay. Clear? Is there any doubt in this?
Just show the slide once more.
Yeah. So this is called minority carrier concentration. Okay. Sorry, majority carrier concentration. This is majority. Okay. Okay. So this generation is nothing but minority. Minority called P(n0). Concentration of hole in an n-type connector at equal to 0, because thermal generation means both electron and hole, right? Right or not?
Right, right.
Right. So after certain time, certain temperature, both electron and hole will increase. The holes will be called minority carrier, which are very small before this temperature. Here is very small. After certain suppose this is 250, 200K, maybe, I don't know. Okay. After a certain temperature, it will go on increasing exponentially. So both electron and hole will go on increasing exponentially. Okay.
Sure.
Okay. So this is called this curve. Everybody will understand, na? This curve. Hello. So
Hello,
let
sir.
me draw the curve very nicely for you. You understood this curve, na? Right?
So what did you ask?
Have you understood this curve?
Yes, yes.
Okay. So let me just before leaving tell clearly. Okay. This is nothing but my okay. N0. This is nothing but my impurity. Okay, ionization. Okay. And there is something called carrier generation thermally. So thermal will be very less. Okay. After certain temperature T will start increasing very more. This will also will start increasing. Right? This is due to thermal generation. Okay, guys, clear?
Yes.
Clear. So this is called, to this point, this point is called extrinsic range. Okay, so in this range, the electrons are only because of the added impurity. Extrinsic means the electrons are added externally, you can say. Okay, this is called extrinsic range. In this range, I have got electrons only because of the added impurity, that is phosphorus in this case. Clear?
Clear, clear.
Clear. Suppose this is suppose you have added 10 power of 15. Okay, 15 number of phosphorus per centimeter cube. Suppose. Okay, so this is nothing but your 15 na. Suppose I have added, okay, donor NDH 10 power of 15 per cm cube. So this will be 15 na. I don't know. Hello? Hello?
Yes, sir.
what I'm telling, suppose this is, I have added 10 power 15 number of donor or nothing but phosphorus per centimeter cube, then this number will be same by 10 by 15 per centimeter cube, na? This, because all the phosphorus have given the electron, right?
Yes, yes.
Or any wrong? Okay. So in the extrinsic range, the number of electron is nothing but number of donor. Fine.
Fine, sir, fine.
Fine. So all of you are getting, na? Now this is called, this range is called intrinsic range. Why? Suppose this is 10 by 15. Okay. So here this is nothing but number of electrons. Okay. Now in this range, okay, suppose because of thermal generation, okay, Ni equal to Pi in this range, okay, in intrinsic range, okay. Guys, you just concentrate, okay, it's very important, okay. Suppose in intrinsic range, see, INTRINSIC, okay, in intrinsic range, in this range, okay, after this I'm telling, okay, clear, guys?
Yes, sir.
So this is my intrinsic range, okay, intrinsic range. Intrinsic range, suppose my carrier due to generation will be equal, suppose Ni is nothing but intrinsic carrier generation, okay, whole, so Ni equal to Pi, suppose equal to 10 power of 17 per cm cube. Clear, guys? Clear. So now what will be my total in total? What will be in total? Already I have this one, okay, Nd, okay, Nd nothing but already I have 10 power 15 plus this Ni equal to the total number of electrons, na?
Yes, sir.
So how much is Nd? Nd is nothing but 10 power 15 plus 10 power 17. Okay.
Yes.
So how much it will be? It will be approximately 10 power 17 only, na?
Yes.
Guys, it will be actually 1.01 times 10 power 17. Clear? I don't know.
Yes.
Clear.
Yes.
So I can approximate this is 1 into 10 power 17 only, na? Right? So what I can say, after a certain temperature in intrinsic range, right, the total concentration of electron will be approximately equal to the thermal generation. That's why it's called intrinsic range. Okay.
Okay, okay.
Okay, guys. So why I call intrinsic range? Intrinsic range, the thermal generation is exponential. Okay. So the total number of concentration of electron will be approximately equal to the intrinsic concentration, and we have lost the extrinsic property. That's why I call we have entered into the intrinsic range. Okay. So this is my intrinsic range. This is my extrinsic range. Okay. And in intrinsic range, my total Ni is equal to Pi. Okay. So what is Pi? Pi is also equal to Ni. Right. So there will be a very like 10 by 17 plus 10 by 15 if you add. It is approximately 10 by 17 only, na?
Yes.
So if I add 10 by 15 plus 10 by 17, it will be approximately 10 by 17 only, right or not? So I can say after a certain temperature, we have entered into intrinsic range where total hole concentration equal to total electron concentration equal to the Ni. Before the intrinsic range, okay, the electron concentration is given by total donor impurity, nothing but Nd. Clear?
Clear.
Clear. All of you clear, guys?
Yes.
Chetan?
Yes, sir. Clear, sir.
Check clear, na? Okay. So with this, just in 5 minutes, I'm going to complete. Okay. This is called N-type, right? We have something called P-type hemimeter. So similarly, how we get P-type? P-type means suppose silicon is mixed with boron. Boron is having only 3 electrons, right? Group 3. This is group 3. group 3. Okay, group 3. What it will go? It will go and keep the silicon away from its side and occupy its space, right? So what will happen? Since it has only 3 electrons, right? It will make 3 bonds. The fourth bond will be vacant. Clear, guys? And this hole created, right, will be revolving around the boron hole, around the boron. Okay. So at a equilibrium in room temperature, what will happen? The number of holes will be equal to number of boron atom per cm3. Clear, guys? And also the hole need very less energy to what will do this boron will do? The boron will accept one electron and it become negatively charged. What will happen? So this boron, suppose the electron come here. Okay, it has accepted one electron, so it created one vacancy, right? So the number of boron atom, whichever number of boron atom we have introduced, all the boron atom will be accepting some electron from the bonded silicon atom and it will be creating some hole. I don't know. So the boron atom will accept an electron from the silicon bond and will become negatively charged, right?
Yes.
Yes.
Right.
Clear. So this is how this is called a p-type semiconductor. Okay, and it gives only hole, not electron, right? This ionization giving only hole, right or not? This is accepting one electron from the silicon bond. So the number of boron atoms equal to number of hole. I'm not getting any electron, right?
Yes. Yes.
So so also you see the number of boron atom all will be negatively charged and they will accept one electron from the silicon bond, become a hole. Okay. Similarly, in n-type semiconductor, the electron will be emitted and the phosphorus will become positively charged. Okay. So the number of electron will be equal to number of charges in the phosphorus, right or not? The total positive charge is equal to total negative charge or not? In n-type semiconductor, each phosphorus atom giving one electron to the conduction band and they become positively charged, right or not?
Right.
So the total positive charge equal to total negative charge or not?
Right.
Hello? See, this phosphorus, it has given one electron and it become positively charged, right? So the positive charge equal to negative charge. Clear?
Clear. Clear.
Clear. So if I ask a question, a n-type semiconductor is electrically negative, electrically positive, neutral. What is the answer?
Electrically negative.
Electrically
Positive, giving electron and becoming positive.
positive. So the total charge of positive equal to total negative, na? How it is electrical positive? The number of positive charge equal to number of electrons. So phosphorus is a bonded atom. It is atom. It will not move. It just gone and set, and it have given one electron. It become positively charged, and the electron is moved. Electron is free, but this phosphorus atom is not free. This is a bounded atom. Okay, so the number of positive charge equal to number of electrons or not?
Yes. Yes.
Then how it is electrically positive?
Sorry. I missed it.
Okay. Similarly, in boron also, each boron atom will accept one electron and become negatively charged. So negative charge equal to total number of holes, right? So each hole that is getting created, electron is moving coming to here. So boron become negatively charged, giving one hole. So the number of holes is equal to number of negative charge in the boron.
Okay.
So all the boron atom will accept one electron, become negatively charged, and give one hole. Right.
Okay.
So a p-type semiconductor is electrically positive or neutral or negative? Hello? 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 Am I audible? Guys, am I audible?
Yes, sir. Hello.
My question is, a p-type semiconductor is electrically positive or negative? Hello.
Uh,
Hello, Sri. My question is, a p-type semiconductor is electrically positive or negative?
it's like the same similar case of N like right, sir.
So what is your answer?
It's neutral.
Neutral, because each boron atom become negative and given one hole. So its positive is given and it become negative. Suppose there is another boron atom. What it will do? It will give one hole and it will accept one electron. So negative is equal to positive. So number of boron atom negative is equal to number of hole. Right? Each boron atom will accept one electron, give one hole. That means negative charge is equal to positive charge or not?
And it's neutral.
Neutral, right? So N-type or P-type semiconductor, they are electrical neutral. Okay.
Okay. Okay.
Okay. So last but not the least, if you see, suppose N-type. Okay. The total number of negative charges is equal to how much? N0. Okay. N0 equal to the donor atom, because each donor atom will be given the one electron, right? Plus this is a concentration from thermal generation.
Yes.
Clear?
Yes.
So the number of electrons equal to number of donor atom plus resistance thermal generation, right? And each donor atom is what? Positively charged, right or not? Because they are given one electron, so they are positively charged or not?
Yes. Yes.
Each donor atom given one electron to the constituent, so they are positively charged, na?
Yes. Yes.
Okay, positive charge. And Ni is nothing but concentration due to the thermal generation. Okay, since Ni is equal to Pi, I can write Nd plus equal to Ni equal to, I can write Pi nothing but by Nn0. I can write none.
Right.
So in total, what I got, total negative charge electron is equal to Nd plus Pi plus Pi, right?
Right.
Pi. So this is my charge neutral equation. Okay, total negative charge equal to total positive charge. Clear? This is called majority carrier. This is Pi is called minority carrier. Minority carrier, right? Right or not? So in extrinsic range Nn0 will be approximately equal to Nd. Right or not? Because
Right.
the generation of this generation is almost zero. Right or not? In the extrinsic range.
Right.
Right. So this is nothing but my bond model. So the bond model will tell you a idea, give you an idea of what is a extrinsic semiconductor, how in N-type electrons are coming, how in P-type holes are coming. Okay. Also it will tell you in extrinsic range the total concentration of electron is Nd. Total concentration of hole in P-type semiconductor will be equal to Na, acceptor atom, right? So this is my N-type semiconductor, this is my P-type semiconductor, right? So the bond model gives me the concentration of electron in N-type semiconductor in extrinsic range and concentration of holes in P-type semiconductor in extrinsic range. Okay, that's all this bond model is giving. Clear?
Clear. Clear.
Clear. So this is all about bond model. Okay, so see how quickly we cover the bond model. Okay, in last time we have taken lot of time, right? So next class also very quickly we will cover the band model. Okay, then we will complete this extrinsic semiconductor. Okay.
Okay. Okay.
So all of you got the idea, na? What is extrinsic semiconductor?
Yes, sir.
Okay. So we shall stop here now.
Okay.
So we will stop here. So next class we will complete the extension conductor maybe in half an hour or so, half an hour 45 minutes. Okay. Then we will jump to what is called carrier transport. So how after generation they are transport, they are giving current to you. Okay. Okay. So next class we will try to complete this carrier transport and extension semiconductor. Okay. Then next class we will start diode. Right.
Right. Right.
Okay. Fine. Okay, guys. Thank you. Have a great day.
Thank you very much, sir.
Thank you.
Thank you.